about the energy required now to remove a 2s electron. Let's say we're removing it from boron +1 versus neutral boron. So in the case of boron +1, what we are starting with is the ion. So we're starting with the 2s electron, and then we're going to 2s1 here. And what we call the binding energy is -2s in B+. This is what we saw in the last slide. And the second case here looks a lot more like what we saw when we were talking about photoelectron spectroscopy, because here we want to remove a 2s electron, but it's actually not the highest occupied orbital. So that's not the one that would naturally come out first, but let's say we're hitting it with high energy light sufficient to knock out all the different electrons, and one that we end up knocking out is this 2s here. So if we think about what that delta energy is, we call that the ionization energy of the 2s. That's different from saying second ionization energy. And that's going to be equal to the negative of the binding energy of 2s in B, in neutral boron. So my question to you is, are these two energies equal? No. All right, good answer. So we can think about why is it that these are not equal. In both cases, we're taking an electron out of the 2s orbital. And it turns out that if we're talking about a 2s orbital in an ion, that means it doesn't have as many electrons in it. So what we're going to see is less shielding. There are fewer electrons around to shield some of that nuclear charge. So what we're going to see is less shielding, which means that it will actually feel a higher Z effective. So even though they're both 2s electrons, in one case it's going to think it's feeling more pull from the nucleus, and it in fact will be, than in the other case. And if it's feeling a higher Z effective, then it's actually going to require more energy to remove that electron, right? It's being pulled in closer and more tightly to the nucleus. You have to put in more energy to rip it away from that very close interaction.